All right. Well, welcome back. Last time we kind of ended the lecture. We were talking about ways to prepare alcohols, and we had gotten to the point where we were looking at some new reactions, and that was the reduction of first ketones and aldehydes, which we said went by an addition. And then we ended the last lecture looking at the fact that esters and carboxylic acids can also be reduced with the reducing agent, which remember these reducing agents we were talking about were hydride reagents. And so you're talking about a nucleophile that's reacting with this electrophilic carbon of the carbonyl. But in the case of the esters and the carboxylic acids, the same thing we saw with the Grignard reacting with an ester or an acid chloride, it would add twice. So you're adding two equivalents of your hydride because this is in fact a leaving group, whether it's a carboxylic acid or an ester. Okay, and so mechanistically, we've already seen this, although I might show you again. But there is one issue. When we go to reduce an ester or a carboxylic acid, if we had an aldehyde or a ketone, both sodium borohydride and lithium aluminum hydride worked well. And also the cyanoborohydride, which is one that you won't commonly see used. But normal, common reducing agents will reduce ketones and aldehydes. Esters and carboxylic acids are different because sodium borohydride does not readily reduce esters or carboxylic acids. And so really the reducing agent that we use for that is LAH. So LAH will. So it is more reactive. And so in general, you might want to put this down, and that is with sodium borohydride, we will be able to reduce ketones and aldehydes, whereas LAH will reduce ketones, aldehydes, and esters and carboxylic acids. Okay, and so LAH is a little more versatile, but again, we said, if you're actually in the lab doing the reduction, sodium borohydride is much easier to use, so you more commonly you'll see it used for aldehydes and ketones, whereas LAH you'll see for esters and carboxylic acids. Okay, so what would this reaction look like if you were putting it on your flashcard? Let's look at some examples. If you're going to use an ester, let's just use a simple ester, and we're going to treat it with LAH, followed by the acid workup. And the result of this, remember, is going to be where I'm adding to the carbonyl carbon, I'm adding two H's, right? Two equivalents of hydride. And then also what's left then is the oxygen that was the carbonyl and is now an OH. So again, I'm forming a primary alcohol, and notice this has left. It's been substituted with the H as a hydride. Okay, and mechanistically, just to remind you, it works the same as what we saw with the Grignard reagents, where you have your H minus from the LAH reacting at this electrophilic carbon of the carbonyl, pushing these electrons up. So initially, the intermediate I form, I've pushed the electrons up to that oxygen. I have my ethyl group, which was present on the ester. I have added this hydride, and then I have my OCH3. And since this is a good leaving group, these electrons could come back in and then displace the leaving group. So initially, I will form the aldehyde, where this was from the first equivalent of hydride reagent. But since aldehydes will also react with hydride reagents, my second equivalent of hydride comes in, reacts at the electrophilic carbon, pushing the electrons out to the O. So then I again form this same kind of tetrahedral intermediate, where now I've added two equivalents of the hydride because a second hydride equivalent has added, right? And then it's just a matter of treating this with the aqueous acid, which protonates this oxygen and gives me the product that we've shown. Okay, same mechanism we saw with Grignards. I just showed you again to make sure. Okay, now what about this example? Well, let's just use a carboxylic acid. And what we're going to do again is treat this with LAH, followed by an acid workup. And what's going to happen? Well, this is going to be the group that's substituted initially, and then the addition, so two equivalents of hydride are going to react. So I'm going to form that alcohol and have the two hydrides that have added. And so that ends up again being a primary alcohol. These are the two equivalents of hydride that have added. This gets replaced. This oxygen is the one that was the carbonyl. Okay. Now, just like we saw with aldehydes and ketones, you have to be aware of the sense that, in that case, if you had an alpha beta unsaturated ketone or aldehyde, we saw that LAH was what you should use because if you use sodium borohydride, you got that mixture of reducing both the carbonyl and the double bond. But in the case of lithium aluminum hydride with alpha beta unsaturated systems, so if you have an alpha beta unsaturated alcohol or ester or carboxylic acid like this, you don't have to worry about it because sodium borohydride doesn't reduce these anyway. So you're always going to be using LAH. And remember, LAH was selective towards the carbonyl reduction. It didn't reduce very much of that double bond at all. And so therefore, in this particular case, what would you expect the product to be? You have your OH, and you've added your two equivalents of hydride. Okay? And so you would form this primary alcohol that is allylic because it is the OH is attached to the carbon that's adjacent to the double bond. All right? And so let's look at this synthetically. We have two reducing agents that reduce carbonyls. One of them, sodium borohydride, only reduces ketones and aldehydes. LAH reduces all of the carbonyl compounds we just talked about. Aldehydes, ketones, esters, carboxylic acids. Okay? And so you can use that in synthesis because that gives you some selectivity. And so, for example, if you have a molecule like this that has two carbonyl functionalities, one of them is going to be a ketone functionality, and the other one is an ester. And so the reactivities of these two are different in respect to the reducing agents, because what I know is if I treat this with sodium borohydride, followed by the acid workup. Remember, it only reduces ketones or aldehydes, so it can only reduce this ketone. It won't reduce the ester. And so in that sense, it's selective. And so you will, in fact, reduce that ketone, but have no effect on the ester. So synthetically, if you want to reduce this group and leave the ester as is, sodium borohydride is a selective reducing agent. Only will reduce that one functionality. But if you take this same compound and you use LAH as your reducing agent, then it's reactive enough to reduce both. So it's not selective. It reduces both of these, and you would end up with this secondary alcohol plus the primary alcohol from the reduction of the ester. Now, I apologize that I'm drawing it out like this, but I'm doing that to emphasize to you the fact that you're losing this OCH3 because you're adding these two equivalents of hydride. Okay? Now, wouldn't it be nice if there were a way of just reducing the ester but not reducing the ketone? There is a way of doing that we will talk about later. But as far as reducing agents, the only selectivity you have is either just reducing ketones and aldehydes in the presence of esters and acids, or reducing both of them. You can't reduce an ester in the presence of a ketone or aldehyde. There's no reagent that will do that. All right? And so that kind of concludes ways to make alcohols. And so once we finish the ways of making alcohols, that brings us to what? Reactions of alcohols. Okay, and we're gonna talk about several of these, and we're gonna number them as we go along. But I just want to give you a schematic to begin with, because there are a lot of things that are both going to be new or review that are reactions we know that will occur on an alcohol. The first of these is we're going to be able to convert these into alkyl halides. Okay. Now I want to emphasize the fact that in most of these cases you can go both directions. We're going to learn how to convert alcohols into alkyl halides, but we also know how to convert alkyl halides into alcohols. So synthetically, this is going to be really useful because alcohols, kind of play a central role in synthesis. We can do a lot with them. We're also going to learn how you can convert an alcohol into an ester. We're going to learn how you can convert it into, the arrow's going the same way. We can also make carboxylic acids from alcohols. We can also make alkenes. We can also make ketones. We can also make aldehydes. And we can also make ethers. A lot of different things we can make from alcohols. And we're going to talk about every one of those. All right. And so again, I'm erasing this because I know that you could have paused and copied that all down if you couldn't get it down in the time that I just had it up. So talking about reactions of alcohols, there are certain types of reactions that alcohols will undergo. And their reactivity, remember we said, kind of like water, alcohols can behave as acids or bases, depending on the conditions of the reaction. And they also undergo different types of reactions based on which bond is breaking in the reaction. So there are basically two bonds, right, that define an alcohol functionality. There's the carbon to oxygen bond and the oxygen to hydrogen bond. Those are basically my two types. The first we will call the OH reactions because they involve breaking the oxygen to hydrogen bond initially in the reaction. The second type is going to be those where we break the carbon to oxygen bond. And you can already tell what the differences are going to be because, just to remind you to plant the seed in your brain, if this alcohol is chiral, breaking the carbon to oxygen bond in the course of a reaction can affect the stereochemistry of the reaction. However, breaking the O to H has no effect on stereochemistry. So those are two main differences between these two before we begin to discuss them. Okay, so let's start by looking at the carbon to oxygen reactions, where that's the bond that breaks. Okay, and we're going to number these. The first of these we're going to talk about is oxidation of alcohols. Okay, and if you remember, just to get you, the transition in place, when we were talking about preparation of alcohols, we talked about taking, ketones and aldehydes, for example, and reducing them to alcohols. Well, now we're going to talk about what happens if you take an alcohol and oxidize it. So that's going to be the reverse reaction. Okay, and so that means that we're going to be taking, in a general sense, we're going to be taking alcohols and we're going to be oxidizing them. And again, I'm going to use O in a bracket to show that we're oxidizing. And when we oxidize, we are removing hydrogen. Okay, and when we do that, we end up with this carbonyl compound. So alcohol goes to carbonyl. And we're going to see that the carbonyl that forms, depends on the reaction. Okay, but like we did with reductions, we're going to talk in a minute about what are the common oxidizing agents. But first, we want to just generally say, if you have a primary alcohol and you do this oxidation, you can form an aldehyde. Or, if you oxidize again, you can form a carboxylic acid. And so basically a primary alcohol has two oxidation states above itself. So one oxidation step is aldehyde. The next oxidation state is carboxylic acid. We're going to see how you can form both of these. Okay? Secondary alcohol, if you do an oxidation, the only thing that you can form is a ketone. Okay? These are terminal functionalities. A ketone is internal because it's a secondary alcohol. And we're also going to see that if you take a tertiary alcohol, by respect of the mechanism, you cannot oxidize it. You get no reaction. Okay, so only primary and secondary alcohols can be oxidized, and I'm going to have three possible products: aldehyde, carboxylic acid, or ketone, depending on the reagent and the conditions. Okay, so what are those common oxidizing agents? Let's look at those. So common oxidizing agents. Okay, these are not to be confused with the reducing agents, which were sodium borohydride and lithium aluminum hydride. These are not going to be hydride reagents. They're going to be things we've seen before, or at least derivatives of that. Potassium permanganate is a common oxidizing agent. So is chromium trioxide. And so is sodium dichromate. Okay, sodium dichromate is not as commonly used. We're going to see that most of the oxidations we look at involve potassium permanganate or some derivative of chromium trioxide. But these are your common oxidizing agents. Okay, so to look at how these agents can be used to oxidize alcohols, we're going to break it down and first talk about reactions of primary alcohols. Okay, and so the first oxidation, because remember there were two oxidation states. We could oxidize a primary alcohol to either an aldehyde or a ketone or a carboxylic acid. So what we're going to talk about first is how do I oxidize oxidation to aldehyde. Okay, and we're going to look at how that oxidation occurs. And so if you have a primary alcohol, you're going to react it with a reagent called PCC. And I know that that's not one of the common oxidizers I just listed, but you're actually going to see that it is. It's a derivative of one. PCC, and by the way, that's the abbreviation that you can use. It's pyridinium chlorochromate. So it's actually just a derivative of chromium trioxide. Okay, and what it's going to give you then is what you would call a partial oxidation to the aldehyde. Okay, so it doesn't oxidize all the way up to carboxylic acid. And so why do you think we would need something like PCC? Because it turns out chromium trioxide would oxidize all the way to the carboxylic acid, and so would potassium permanganate. So we need a reducing agent that is not reactive enough to oxidize this all the way to the carboxylic acid. So it's a partial oxidation. And we've talked about this before with things like Lindlar catalyst. You know, if you don't want something to be as reactive, you poison it a little bit so it's not as reactive. And so that's what we do with PCC. It's basically chromium trioxide, but you formed a pyridinium salt of it. And so you have, remember, pyridine is this aromatic ring where a nitrogen has replaced the carbon. And so you have this pyridinium salt where you have a protonated pyridine, and then the counter ion is the chloride, and it kind of makes this chromium trioxide less reactive. So it's not as powerful an oxidizer, so it only oxidizes one oxidation state. Okay? So if you want to take a primary alcohol, if you treat it with PCC, you will form the aldehyde. Okay? But you can also oxidize it all the way. So let's say oxidation to the carboxylic acid. And here we can take our primary alcohol, and let's just use this example. And we're going to treat it with chromium trioxide, so the non-poisoned. So chromium trioxide. Now, usually when you use chromium trioxide, you're also using it in sulfuric acid which is just part of the solvent, water, and acetone. Remember from last semester, acetone is commonly used when you have organics and you have aqueous systems. Acetone is miscible in both organic and aqueous solutions, so it kind of ties things together. But this is the standard set of reagents. This is one thing you could put on your flashcard. Primary alcohol, these are the reagents for chromium trioxide, and what it does is it's not a partial oxidation anymore. It oxidizes all the way to the carboxylic acid. You know, and this concept isn't new, right? When we did oxidative cleavage of alkenes and alkynes last semester, we talked about how some of them gave aldehydes, some gave carboxylic acids, depending on the conditions. That's what you're seeing here. Okay, but there is one little caveat here. It's not really a caveat, I guess. There's one thing that's the conditions for chromium trioxide to oxidize a primary alcohol all the way up to carboxylic acid. This list of reagents was actually discovered by somebody named Jones. And so we call it Jones's reagent. Okay? Because back then they used to name reactions after the people that discovered them. And so Jones's reagent, believe it or not, you can write this on the arrow. You can just write Jones's reagent. And this is what it means. It means you're using chromium trioxide and sulfuric acid. Okay? And so with primary alcohols then, PCC, poisoned, Jones's reagent oxidizes just to the aldehyde. But using chromium trioxide all the way from the primary alcohol to the carboxylic acid. All right? Well, what happens then if you have secondary alcohol? And so let's call this 3. And so that's where you're going to have something like this. Okay, if you remember from our table, if you have a secondary alcohol, there's only one thing you can oxidize it to, a ketone. There's no partial oxidation, right? And so it doesn't matter whether you use Jones's reagent, because it will oxidize all the way up to the ketone. Okay? But you also, if you have a secondary alcohol, you can use PCC, and that will oxidize to the ketone. So it doesn't matter which oxidizing agent you use, secondary alcohols always get oxidized up to the ketone. All right? What about tertiary alcohols? What did we say about tertiary alcohols? No reaction. Why do tertiary alcohols not oxidize? Why is there no reaction? I wonder what would answer that for me. Oh, the mechanism. So let's look at the mechanism of this. For any alcohol that you have, this is what the mechanism looks like. Let's go ahead and pretend we're showing stereochemistry. So there's an alcohol. When you treat it with chromium trioxide, and potassium permanganate, we're not going to worry about mechanistically, but it works the same way, as does PCC. Because what basically occurs first is when you react the OH with one of these chromium reagents, you form this intermediate. Okay? And notice here I put an H. And I didn't over here. But I'm going to do it now. Because what I'm basically showing is, if this were a tertiary alcohol, these would all be R groups. But if it's a secondary or a primary, I'm going to have at least one H attached to the carbon which bears the OH. And so there's always going to be at least one H there, which is important because the way this oxidation works is once you form this intermediate, it's really just an elimination where the electrons from this carbon to H bond move in to form the carbonyl and it displaces the chromium, and you end up forming this plus this new chromate salt plus H3O plus. Now, so you form this. So the important thing is for the elimination to occur, there has to be at least one H on that carbon. And the only way that's going to happen is if this is either primary or secondary. Okay? So hopefully that explains that. So those are the different oxidations I can do, which are reactions of OHs. All right? And notice the reaction is occurring at the C to O bond. The fifth reaction is dehydration. And so you can dehydrate an alcohol, and when you do that, what's the result going to be? I mean, this is something that is really review. So in general, what I'm saying is what happens if you have an alcohol like this, and I decide that I'm going to do a dehydration. In a dehydration, you're doing what? You're removing water. And if I remove water from this, I am basically doing an elimination. And eliminations are going to give me what? A double bond. So you're basically in the dehydration, you're forming an alkene plus water. So these are just elimination reactions. We've already talked about elimination reactions. So these are going to be E1 or E2 reactions. Nothing really new. Okay, and so what we just need to look at is reagents. Well, one way you can do this is in an acid catalyzed reaction. And that's where you have something like this, an alcohol, and I'm going to treat it with H3O plus, and it's going to give me the alkene. Okay, and remember, this is Zaitsev's rule that governs this. So I'm drawing this product because this is the more substituted double bond. Okay, and we remember Zaitsev's rule from last semester. So this is going to be the major product that forms. Okay, and so this works really only for tertiary systems. And the reason for that is it goes through an E1 mechanism. And we remember that from last semester. E1, remember, is the elimination that looks very much like SN1. And that is, if we look at the mechanism of this reaction, to say that it's E1 means that I'm going to have the reaction between the protonated water. That's an acidic proton. This is the nucleophilic oxygen. Remember, you put H3O plus in the presence of an alcohol. What do you always do? You protonate it. We've even seen that already this semester. We were talking about how alcohols can behave as Lewis bases. And so I initially protonate that. Okay, and when I protonate that, I've made this a good leaving group. So it's going to spontaneously leave. That, remember, is the characteristic of an E1 reaction. Your leaving group spontaneously dissociates, and it leaves the carbocation. And the reason this works well for tertiary alcohols is it leaves a tertiary carbocation. Okay, and so once that forms, then it's just a matter of having water come in as a base, and it's going to take off this proton. Electrons are going to move in. You know, folks, this is an E1 mechanism. We've talked about them already. This is review, and the result is that I formed that alkene. Okay, so this reaction works with, oh, and by the way, I almost forgot. If water's taking the proton off, I'm forming H3O plus. So that's demonstrating that the reaction is acid catalyzed. Okay, so this works for tertiary alcohols only because it goes through an E1 mechanism. Okay, but what happens if we have a primary or secondary alcohol and we want to do the same dehydration reaction? Is there a way we can do it? And the answer is yes. So this is B under dehydration, and it's using a reagent called POCl3, okay, phosphorus oxychloride. Phosphorus oxychloride. And it's going to work with primary and secondary alcohol. So it's going to allow this dehydration. But you know, it also works for tertiaries. It doesn't discriminate. It'll do it for any of them because it goes through an E2 mechanism. And remember, E2 mechanisms, it doesn't discriminate. It's ubiquitous. It'll work on any system. Okay? And so in order for this reaction to occur, as you're looking at me draw the general reaction, think about what you think needs to occur mechanistically for this reaction to undergo an E2 mechanism. So remember, OHs are not good leaving groups. And so if I have just a simple secondary alcohol like this, I can treat it with POCl3. And here are the conditions you'd have on your flashcard. You're going to use pyridine as a solvent. And it's usually done at low temperature, but it'll work at room temperature also. And the result of that is the formation of the alkene, and it's a really good yield, about 96%. Okay? And so how is this going to occur? Well, the first thing to point out is unlike acid-catalyzed dehydration, pyridine is actually basic. So you're basically, you're using basic conditions. I can't say basically using basic conditions, but it's a basic reaction and as opposed to acidic, okay? And mechanistically, how would this work? All right. Has anybody thought in this time about what might need to happen in the mechanism? Well, in order for a primary or secondary alcohol to undergo dehydration, it's going to be an E2 mechanism, so we need that OH to be converted to a better leaving group. And we've seen this before. Okay, and so that means if I use that same example where I have my secondary alcohol, and I'm going to react it with that phosphorus oxychloride, but I'm going to actually draw this out like an organic chemist would, where I have my 3 chlorines attached to the phosphorus and then a phosphorus double bond O. So this is what the reagent looks like. So looking at it like this, you can clearly see that this is going to be my nucleophile, and this phosphorus is the electrophilic center. It's got all these chlorines and an oxygen on it. Electron density is being drawn away from it. So what happens initially is that oxygen comes in and it reacts with the electrophilic center. Now, again, I keep stressing to think about the general, broad picture here. How often do we see nucleophiles reacting with things that have double bond oxygen to them? We just saw that with all the carbonyls. Think about the fact that this is a very common thing. Nucleophile with this electrophilic center, which is going to do what? kick those electrons up to this oxygen. So I can draw initially an intermediate where I've done what? Where I've formed a new bond between this oxygen and that phosphorus. That kicked the electrons out to that oxygen, and it has left 3 chlorines on here. Well, now these electrons can close back in. Does anybody see how this is similar to Grignards and hydrides reacting with esters? Electrons come back in, and then it can kick something off, because these are all good leaving groups. If it kicks this off, you're just back to where you were, the reversible reaction. But it could also kick off a chlorine. And if it does that, it would form this. And by the way, did anybody see that I left a plus off? Sorry. There's a plus on that oxygen. Okay, which is still there. So then now I have my phosphorus, but now I have a double bond O, and it's bound to my 2 chlorines. Okay, so does anybody see what's going to happen next? I have a Cl minus that has come off. Okay, that can pull this proton off. Which gives me this intermediate. And so what I've basically done is turned this OH group into something that's a really good leaving group. Now it just takes something like pyridine, which is a base, pulls this proton off, electrons come in to form a double bond, and it kicks off that as a leaving group. And the result of that is the formation of the alkene. And I'm sorry, just to be clear, I'll put it there. So POCl3 creates a good leaving group, which can then be eliminated through an E2 mechanism to give the alkene product. And this will work equally well if this is primary, secondary, or tertiary. Okay, so that's a dehydration reaction that works well, alcohol to alkene. Okay, we've seen 2 ways, acid catalyzed and POCl3. And that brings us to our next reaction, which is conversion of alcohols into alkyl halides. So you can see synthetically how this might be a useful reaction. And by the way, we're still in reactions that are classified as CO reactions because the reaction is occurring at the CO bond. Okay, the first conversion of alcohol into an alkyl halide is going to be if we have a tertiary alcohol. And why do we always have to break this down into tertiary versus primary and secondary? We'll see, because it has to do with the whole, you just saw a minute ago it had to do with whether it was E1 or E2. But if you're doing a substitution reaction, it's now going to be whether it's SN1 or SN2. And that has to do, remember, with the substrate, the substitution. All right? And so if you have a tertiary alcohol, you're able to simply take your tertiary alcohol, and I'm just going to do a generic tertiary alcohol. You can treat it with a mineral acid like HCl, and as we normally would say, we can use HCl or HBr as my mineral acids here. And what's going to happen when you put an alcohol in the presence of an acid? We've seen this a zillion times, right? You protonate the OH group. And so when you do that, you're going to form this intermediate. Still have my generic tertiary alcohol, but now I've protonated the OH. And when I do that, it becomes a really good leaving group. And so I spontaneously dissociate that water, and that leaves me with the carbocation. Now, is there anybody knows that this is basically the mechanism we went through with dehydration a second ago? Because that was an E1 elimination. This is going to be an SN1 substitution. Remember, they go through basically the same first step of the mechanism. So this is all review. We've seen this before. And once this happens, remember there's a Cl minus that we formed right here. So that's this nucleophile reacting with the electrophilic center. And the result of that is I've substituted my chlorine onto the carbon. So I've gone from an alcohol to an alkyl halide, going through an SN1 mechanism. Okay, so as long as your alcohol is tertiary, you can simply treat it with HCl or HBr and convert it into the alkyl halide. But now, again, this is going to sound redundant. Now I'm moving, well, what about the case of primary and secondary alcohols? Now I'm going to be doing not SN1 reactions anymore. Now I'm going to need to do SN2, because that's what occurs on primary and secondary centers, remember? And so just like with the dehydration, I need to figure out a way of making the OH a better leaving group, because that will allow the substitution to occur. And so using a primary alcohol as the example, I'm going to have to use reagents that make the OH a better leaving group. And we can do that with two different reagents. SOCl2, thionyl chloride, or PBr3. Now, I'm pretty sure that we looked at these briefly last semester, but I'm showing you these again, because basically what happens in the case of thionyl chloride is going to convert this into the alkyl chloride, and in the case of PBr3, it's going to convert it to the bromide. Okay, and that'll work for primary, secondary, and yes, it will work for tertiary, but it's usually not what you use. Usually you use the mineral acid for the tertiary. Okay, and so I'm going to let you all think, because this might be something that you may want to ask in one of the sessions at 11. But the mechanism of this occurs really just like POCl3 did for the most part, because I'll just show you this to get you started. Thionyl chloride has this structure. And so mechanistically, remember, if you're making a better leaving group, all you're doing, in essence, is attaching the S double bond OCl to your O here, making it a better leaving group, and then the chlorine that comes off as the nucleophile and comes in and reacts. Look at those mechanisms on your own, because I think you can figure it out, because it's just like POCl3, and that'll give you a chance to maybe have something to come with a question next time. Okay? Oh, and by the way, PBr3 is a stunning structure. And so mechanistically there, again, nucleophilic O is just for reacting with the phosphorus kicking off a Br. That forms something that's a better leaving group, and that Br minus just comes in and substitutes. Okay, so we're getting to the point of where we've been talking about 50 minutes. So I'm going to kind of just transition into the next topic where we'll pick up next time, and that is we can convert now to reactions at the O to H bond. So these are going to be different than the ones we just went over, in the fact that when we do the reaction, the only bond we're going to break is this one. So I'll give you an example, and we'll pick up right here next time. I have an alcohol, and I'm going to react it with tosyl chloride, which is something that we mentioned last semester because it was a really good leaving group. And we're going to react this in the presence of pyridine, which is a very common thing that you see when you're displacing chlorines in reactions because you often are forming HCl. And pyridine is kind of like an acid sponge. It forms a salt with the HCl, so it kind of removes it from the solution. But what we're going to see happen is when we do this reaction is we will actually substitute the tosylate onto the alcohol. And so notice we're not breaking the R to O bond, the carbon to oxygen bond, we're breaking the O to H bond when we do this reaction. And in this particular case, what we're going to see when we do this reaction, we're making this O a better leaving group, okay, for it to undergo other reactions. So what we'll start with next time is we'll mechanistically look at how this reaction is occurring. Since it's a different type, it's an O to H type of reaction. And then after we look at that mechanistically, we're going to see about how this different type of reaction gives us totally different stereochemistry than we've been seeing in the other reactions. And so with that, I will stop and we will begin next time right at this point.